Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Dan salam sejahtera everyone. Okay, we continue with the video number 2 regarding the chapter 1, valence bond theory. Now, subsection of hybridization of atomic orbital. So in this section, you have to understand what is the hybridization, why we hybridize the atomic orbital. In the previous video, we talking about the overlapping of atomic orbital, s orbital, p orbital, d orbital, and so on and so forth to show the formations of chemical bonding. But in this particular section, we're gonna to hybridize the s orbital, p orbital, d orbital, and also f orbital. We try to hybridize these four orbital to form new orbital. So it's mean that hybridization is a process of mixing this atomic orbital to form new orbital. First of all, this is the explanation about the hybridization. Hybridization is the process of mixing the two or more atomic orbitals to form a new set of orbital. We call it hybrid orbital. By mixing this, we will produce hybrid orbital. The process of mixing, we call it hybridization. The hybrid orbital that form from the mixing have different shape compared to the original atomic orbital. If you still remember the atomic orbital of S is round, atomic orbital of P is look like the spin, is look like the pin bowling, or it's look like the chromosome. Okay, but when we hybridize those atomic orbital, it will form another different shape. So pay attention how the shape between the hybrid orbital, the original atomic orbitals are different. Okay, they have 5 types of hybrid orbital. Ada 5 jenis hybrid orbital. The first one is sp. When we say sp, so it's meant that we mix s plus p. We mix this to form new orbital. We call it sp. Another orbital is the sp2. It's meant that 1s we mix with 2p. The third hybrid orbital is sp3. So you can predict 1s and also 3p. Okay, so the fourth atomic orbital, the hybrid orbital, is the sp3d. Sorry, this one is should be 3. Another one. So sp3d s 3p. Sorry, it's a bit slow because scrolling this. And 1 p orbital. Okay, the last type of hybrid orbital, we call it sp3 d2. S 3p, we mix 3p and 2d. Okay, as I mentioned just now, the shape of this hybrid orbital will be different from the original of atomic orbital. Let's say we have s orbital. The atomic shape is like this, round. If we have p orbital, we can have this look like this, the pinballing or the chromosome. So we have orientation of px. We can have py, and also we can have pz. Because the number of electrons, total number of electrons for the p orbital is 6. Okay, the number of electron, the maximum is 1, 2, 3, 4, 5, 6. This is x, px, this is py, and also this one is pz. Okay, so we learned this previously. So the shape of hybrid orbital is totally different is compared to the original atomic orbital before mixing. So the shape or the geometry of the hybrid orbital will be determined or depending on the electron domain geometry. For example, this is sp 1s, 1s, 1p. So have electron domain of 2. So geometry is linear. So whatever atom have this hybridization, for example, we call it X, X atom. So the geometry should be linear. Linear. It's look like this. It's look like the p orbital is linear. So the sp2, 1s and 2p, 1 plus 2. So it's meant that 3. When the electron domain of 3, we call it trigonal planar. Trigonal planar is like this. So if you want to draw the hybrid orbital, let's say the central atom is X. So we should draw the trigonal planar. Okay. Same goes to the sp3. sp3 is 1 plus 3. So it should be 4. 4 electron domain, meaning that tetrahedral. So let's say we have X atom is the central atom. We draw the sp3 in the tetrahedral geometry. 1, 2, 3, and 4. Okay. For the sp3d, sp3d is the 1 plus 3, 3p plus 1d. So it's 5. When it's 5, meaning that it's trigonal bipyramidal. So how the trigonal bipyramidal is look like? If you still remember, trigonal pyramidal is like this. Trigonal bipyramidal. So if we have a central atom of X with hybridization of sp3d, so we can draw the trigonal bipyramidal. My drawing is not so nice, so you can draw better than me. Okay, trigonal bipyramidal. It looks like similar. Last but not least, the hybrid orbital of sp3d2, 1s, 3, 2d. So in total of 6. Okay. So in total of 6, so this means that the geometry is octahedral. Okay. So how the octahedral look like? This is the octahedral. So let's say we have an X atom, any atom, central atom with octahedral geometry. So we just draw the octahedral. As you can see, the shape of SP, SP2, SP3, SP3D, SP3D2 are different compared to the original atomic orbital that we mix S with P. So, of course, you have to remember the 5 types of hybrid orbital: SP, SP2, SP3, SP3D2, and also SP3D2, SP3D, SP3D2. And also try to understand what is the SP all about. Is S plus P, S with 2P, S with 3P, S with 3P1D, and S with 3P2D2. So the last important point is you have to remember the shape. The shape is depending on the electron domain. So if the electron domain of 2 is a linear, so the linear is like this. If electron domain of 3, so it's a trigonal planar, so the shape is like this. If the electron domain of 4 is supposedly is tetrahedral, so the geometry is like this. And if the electron domain of 5 is should be trigonal bipyramidal, so the geometry is like this. Last but not least, if the electron domain of 6, the geometry is octahedral, so the way it slopes is like this, octahedral geometry. Okay, I hope you can understand this one. So don't to be forget, the hybrid orbital determined using electron domain geometry. So you have to count the electron domain, and then from the electron domain, you can tell what is the geometry. How to determine the types of hybrid orbital of the central atom for a particular molecule? It's very easy. As I mentioned, we have to calculate how many electron domain around the central atom for whatever molecule. So as we learned previously, electron domain is a lone pair plus bonding pair. So we have to count. We have to identify what is the electron domain, how many lone pair, how many bonding pair, and then you can decide. If the electron domain of 2, the hybridization is sp. If electron domains of 3, hybridization is sp2. If the electron domain is 4, hybridization is sp3. If the electron domain of 5, hybridization is sp33. Last one, if the electron domain of 6, hybridizations become sp3e2. Okay. Selain identifying the type of hybridization, drawing the geometry of each hybrid orbital, we should be able to explain the energy diagram of valence electron for the central atom for each hybridization. The basic or the fundamental of drawing the orbital diagram, energy diagram of valence electrons are similar is we did for the hydrogen, chlorine, oxygen, or nitrogen. Okay, as we did before, in order to draw the in order to draw the energy diagram of valence electron, first we have to identify what is the central atom, and then check from the periodic table how many total electron. After you confirm the total electron, you have to write the electronic configuration 1s2, 2s2, 2p3, blah, blah, blah. And then from that, after you complete the electronic configuration, you have to identify what is the valence electron. After you confirm the valence electron, then you can draw the energy orbital diagram of valence electrons. So we will go one by one explanation about the energy diagram of valence electron for all the hybrid orbitals. The first hybrid orbitals is the sp. We know sp hybrid orbital is mixing s with p. Let's say this is the example of molecule, and then you can draw the Lewis structure nicely. After you draw correctly, you can decide how many lone pair around the central atom. This is the central atom. You should be can tell what is the lone pair, how many lone pair. In this case, it's 0 lone pair, but they have one bonding pair and two bonding pairs, single bonding, single bonding. So we have two bonding pair. So electron domain of 2. When the electron domain of 2, the geometry is linear. And then we know electron domain of 2 hybridization is sp. So now we have to draw the electronic configuration, the energy orbital diagram for the valence electron of the central atom. So we check from the periodic table what is the total electron of beryllium. Okay, we have to draw the energy orbital diagram. So from the from the periodic table, we know a total electron of beryllium is 4. Okay? Okay. We write the electronic configuration first. Beryllium is 4, so it's meant that 1 S2, 2 S2, 1 S2, 2 S4. 1 S2, 2 S2. So this is the valence electron of beryllium. 2 valence electron. This is why from the Lewis structure, we know one electron will be sharing with another chlorine, one electron will be sharing with another chlorine atom. This is why this is a 2 valence electron. So when we draw the energy diagram of valence electron for the central atom, in this case is beryllium. So this is the energy level diagram. It's a similar with we did before that we did for the hydrogen or the oxygen or nitrogen. But in that way, we just ignore the energy level of the orbital. As we did before, we do it in the horizontal line. Like hydrogen, we say like the hydrogen, we say one hydrogen here, another hydrogen here, and then one hydrogen carry one electron, another hydrogen carry one electron, and then they share electron to form H2. The same fundamental, but now we try to draw it nicely, the energy level diagram of valence electron. Is we found the valence electron for the beryllium is 2, so 2 S2. So this is the energy axis. So we have 2 S2. You can write 2 or you just ignore 2 also can. It's up to you. 2 S2, so 2 electron. So but if you want to draw this one 1s1 also can, but it's no meaning because 1s1 is should be in the bottom. 1s1. You can draw or you just ignore because we just focus the valence electron. Only valence electrons are involved in the formation of chemical bonding. All right. Okay, why we have this p orbital? If you still remember that the things that you study in the secondary during the SPM matriculation or the foundation during the foundation or diploma, this is about principle. 1s. The second orbital we have 2s and 2p. This is why second orbital it come together with 2s and also 2p. And third orbital it should be 3s, 3p, and also 3d. Okay, we back to this energy level diagram of the Be atom. Okay, because Be is the central. Okay, as you can see, this one is 2s2, 2s2. All these orbitals are fully occupied. So it's meaning that no single electron. So as we mentioned, only single electron will be a partner or will be coupled with another electron from another atom in order to form the chemical bonding. So if this beryllium not undergo the hybridization, the valence electrons is fully occupied, 2s2. So no formation of bonding because the no single electron. So this why we need hybridize. We need to mix two orbital to provide single electron. So if we decide from the Lewis structure, we identify we have to do the sp hybridization. So we have to transfer one of the electron to the p orbital to form s and p. So when we do the mixing to form the s and p, so the energy level for s orbital and p orbital are different compared to the sp energy orbital. After we mixing this S mixed with P, so it become single. So one Sp in another Sp, and these two orbital remain empty. So we call this unhybridized unhybridized orbital. So then if we have this single, then we can form this will be coupled with Cl. This single can couple with another Cl in order to form the BeCl2. But if we reluctant to do the hybridization, the valence electrons are fully occupied into s orbital. So by using the valence Von theory explanation, the no bonding can be formed because no single electron. This why we have to mix the atomic orbital to provide single electrons accordingly. Okay, so now we can draw the geometry. Okay, this one is the hybridized, this one the isolated. Isolated meaning before the mixing. So how to draw is we confirm the geometry is linear because it's sp electron domain of 2. So linear, beryllium in the middle. So linear, we just draw the linear in the linear way. Okay, this is SP. And then overlap with Cl. Cl also P orbital. Okay, overlap. Cl also p orbital. Okay. In the electron domain or the region of overlapping, we have spin up, spin down, and also spin up, spin down. So, according to valence bond theory, this molecule is the overlapping of p orbital with sp, sp hybrid, overlapping between the p orbital with sp. Chlorine is a p orbital, but the beryllium is the sp orbital. So this is the way to draw the geometry of sp hybrid orbital. Okay, so this is the geometry, the diagram of hybridization is a linear. Okay, similar, the same. Okay, so we can conclude in order to form two covalent bonds with chlorine atoms, two with chlorine. Okay, that one that we did before. Okay. In order to form two covalent bonds with chlorine atom, beryllium atom must supply two single valence electrons. This one only can be achieved by using the sp. If we don't proceed with the sp hybridization, the energy diagram only have no single electron. Okay, so the two chlorine atoms are covalently bonded to beryllium atom through the overlapping of p orbital of chlorine and also sp orbital of beryllium. Okay, all right. Okay, moving forward to a second type of hybrid orbital, sp2. 1s, 2p, spp, sp2. Let's say this is the example, BF3. After you draw the Lewis structure, you find out on the central atom, beryllium don't have any lone pair, but they have three pair. One pair, two pair, second pair, third pair. Okay, so 0 plus 3 is a 3. So when 3, electron domain of 3, the geometry is trigonal planar, like this. And then the hybridization is this sp2. Okay, hybridization is sp2 because of electron domain of 3. So same procedure or same step, you have to check the total electron of boron from the periodic table. During the test or during the final assessment or during the quizzes, the periodic table supposedly provided. So you should know how to read the periodic table. Okay, let's say from the periodic table, the boron, the total electron of boron is 5. You can check your periodic table. Okay, so you can write the electronic configuration for this total electron of 5. 1s2, 2s2, and also 2p1. So atomos orbital will give 3 valence electron. This why we have one electron share with F, one electron share with F, another electron share with F. This why we have 3 valence electron. When we draw the energy level diagram for the valence electron, it is 2s2, 2s2, and also 2p1. So this is 2p1. Before we do the mixing, we only found only one single electrons. So meaning that only one can form bonding with F because only one electron is already full. This one will be shared with another electron for F. So if we don't proceed with the hybridization, so the formation of BF3 cannot be happen. That's why we have to mix the orbital, or we have to hybrid the orbital in order to provide three single electron. As we agreed, it should be sp2. So we have to transfer one of these electrons to here in order to have one S, one P with another P, sp2. Okay. So now we have three single electron. After we hybridize sp2, we have three single electron. This one is remain unhybridized. So when we have three single electron, then we can form one electron combined with fluorine, another electron combined with second fluorine, and also another electron combined with third fluorine. After we hybridize, we can have three single electrons. If we don't hybridize only one, so only one fluorine will be bonded into the boron. So it's meant that this molecule is not happen. Of course, by using the Lewis structure, we can show the formation of the three valence electron, 1, 2, 3. But by using valence bond theory, we want to show which orbital involved in the formation of bonding. Is it s orbital, p orbital, or hybrid orbital? And then after we do the energy level diagram, we agreed this isolated B atom have to hybridize in order to provide enough single electron in order to form the F3. Okay, so how to draw? As we agreed, this is electron domain of 3. The geometry should be trigonal planar. So it's very simple. We put P in the middle, so we do the trigonal planar. And then that trigonal planar will be overlapping with F. F is the p orbital because the electrons, valence electron is a p orbital. F. So we draw it nicely on the trigonal planar geometry. F. Okay. So we know in the overlapping area, they have a spin up, spin down, and also a spin up, spin down, and also spin up, spin down. So according to the valence bond theory, in the BF3, the overlapping between P with sp2. Same goes to here. P with sp2. Same goes to here. S with, sorry, P with sp2. Okay. So this is the geometry. It's the same trigonal planar boron, and then like this. sp2, sp2, sp2 overlapping with p orbital of f, p orbital of f, p orbital of f. So that's for the sp2. Same explanation. In order to form three covalent bonds with fluorine atoms, boron atom supply 3 valence electron. This can be done by using sp2. The 3 fluorine atoms are covalently bonded to the boron atom through the overlapping between p orbital of F and the sp2 orbital of the boron ring. Okay. We move to the third hybrid orbital, which is sp3. Let's say this is the example methane. After we draw the Lewis structure, uh, we find out the central atom. It containing 0 lone pair, and then how many bonding pair? 1, 2, 3, 4. 4 bonding pair. So electron domain of 4. So the geometry, it should be tetrahedral, and the hybridization supposedly is sp3. Okay, geometry is tetrahedral. Hybridization is sp3. So similar, you have to draw the energy level diagram of the central atom, carbon. Total electron of 6. 1s2, 2s2, and also 2p2. So this is outermost orbital. They have 4 valence electron. This is why 1 valence electron, 2nd valence electron, 3rd valence electron, 4th valence electron. Yeah, this is agreed for the Lewis structure. But how about the valence bond theory? Which orbital that involved in the formation of bonding? So first, after we write the electronic configuration, identify the valence electron, we have to draw the energy level diagram for the isolated carbon atom. From here, we know the valence electron is 2s2 and also 2p2. 2p2. Again, if we don't proceed with the hybridization, only 2 electrons are available, single electron available to form the covalent bond. Only 2. How about another 2? This is why we have to mix, we have to hybridize. So when we hybridize, we know the hybridization supposedly is sp3. So in order to provide 4 single electrons, we have to hybridize using sp3. So we have to move this electron into here. And then after that, we can get the 4 single electrons via sp3. So this electron combined with 1 hydrogen. This electron share the electron with another hydrogen. This one will be shared with third hydrogen. This one also can be shared with fourth hydrogen. So by using the valence bond theory, we can explain further the formation of bonding. Okay. So in terms of geometry, it's a tetrahedral. So we just draw it in the tetrahedral way. Carbon is a central atom. So tetrahedral is like this. It's like a tetrahedral. Okay, but very careful with the terminal atom. The terminal atom is hydrogen. Hydrogen is the s orbital, so it should be round. It's not p orbital. Hydrogen s orbital, s orbital, s orbital, and also s orbital. Every hydrogen is not h orbital. Hydrogen, what? Hydrogen, hydrogen, and also hydrogen. In every overlapping area, they have a spin up, spin down, spin up, spin down, spin up, spin down, and also spin up, spin down. So according to the valence bond theory, this bonding is the overlapping between the s of hydrogen with the sp2. Same goes to here, same goes to here, and same goes to here. sp2 overlap sp2, sorry, sp3. S with sp3, S with sp3, S with sp3, S with sp3. So this is the diagram of the tetrahedral. And then overlapping with the s orbital of the hydrogen. Okay. So in order to form four covalent bonds with hydrogen atoms, the carbon must supply four single valence electrons. This can be done using sp3. The four hydrogen atoms are covalently bonded to the carbon atom through the overlapping between the s orbital of hydrogen and the sp3 hybrid orbital of the carbon. Okay. We go another example of sp3. In this case, ammonia. If you can still remember the Lewis geometry, Lewis structure of ammonia is like this. Ammonia with three hydrogen and one lone pair. So the central atom containing one lone pair and how many bonding pair? 1, 2, 3. So electron domain is 4. So when the electron domain of 4, the hybridization is sp3. But the geometry is a bit different because electron domain of 4 is tetrahedral. Because of one lone pair, it's not longer tetrahedral. It become trigonal. What? Trigonal? Trigonal apa? It's not trigonal planar. It's not trigonal bipyramidal. It's trigonal pyramidal because only one pyramid. Pyramidal. Okay. Okay. Trigonal bipyramidal because of one lone pair. So how to draw the energy diagram? Same fundamental. The central atom is nitrogen. So nitrogen is the 7 total electron. So electronic configuration is 1s2, 2s2, and also 2p3. This is why the atomos orbital, it has 5 valence electron. 3 electron, 1, 2, 3 are using to form the single bonding with the hydrogen. The leftover 2 electron become a lone pair. So in the energy level diagram for the nitrogen atom, we know the valence electron is 2s2. So 2s2. And also 2p3. 1, 2, 3. Okay. So before we mixing, we double check. Okay. This is a 3 single electron. So meaning that is enough to form 1 hydrogen, enough to form with a second hydrogen, enough to form the third hydrogen. But we still have to do the hybridize of sp3 because one of because it have one lone pair. So in this case is a bit different. No need to transfer one of the electron to another orbital because it's enough. We have 3 single electron to form single bonding with 3 hydrogen, and then this 2 electron is remain is 2, and these 2 become lone pair because lone pair is 2 electrons. So after we hybridize into sp3, so we have lone pair, and then we have 3 single electron to form bonding with 3 hydrogen atom. Okay. So geometry same, a trigonal bipyramidal, nitrogen in the middle. We have lone pair, and then we have the pyramid, trigonal pyramidal. Overlap with what? Overlap with hydrogen. Hydrogen is the s orbital. Hydrogen, hydrogen, you can draw nicely. And also hydrogen. Every overlapping area, they have up and down, spin up, spin down, electrons, spin up, spin down, spin up, spin down. This represent this electron up and down, up and down, up and down. So according to the valence bond theory, it should be overlapping between S and sp2, sp3. S sp3, S sp3, and also S sp3. So this is the geometry. Is the trigonal pyramidal. sp3, one lone pair, and sp3 overlap with s orbital, sp3 with s orbital, sp3 with s orbital. Okay. Another example of sp3 but different molecule, H2O, water. H2O, this is the Lewis structure. We find out the 2 lone pair, 1, 2, and 2 bonding pair. So electron domain of 4. So hybridization sp3. The geometry tetrahedral, electron domain 4 tetrahedral, but we have 2 lone pair. So the geometry is no longer tetrahedral, it become band. Okay, it become band. So what is the total electron of oxygen? Is 8. So we write the electronic configuration. 1 is 2. Okay, 2 is 2. And then 2p 4. 4, 6, 8. So the autonomous orbital, they have 6 valence electron. This why we have 1, 2, 4, 6 valence electron. So energy level diagram of oxygen 2s2, 2p4, 1, 2, 3, 4. But you can see only two single electrons is enough to form with one hydrogen with another hydrogen, but we have two lone pair. This can be lone pair, this can be lone pair. So we have to proceed with hybridization to form the sp3. Seems goes to the this molecule similar like the ammonia. No transition of electron. These two remain as the lone pair. Lone pair for this one, lone pair for this one. And another two will be share its electron with another hydrogen, and this one will be shared with another hydrogen. So in terms of geometry, same oxygen in the middle, and then we have tetrahedral, but we have two lone pair, and then we just have this one. So these two will be overlapping of hydrogen. Hydrogen is s orbital. This will be overlap with h orbital. Okay, and spin up, spin down. So according to valence band theory, is supposedly S overlap with sp3. Same goes to here, S with sp3. So this is the geometry band tetrahedral, but due to the presence of two lone pairs, become band. Okay. We go the second last example of hybrid orbital is P3D. Very same approach. Chemical formula, Lewis structure, identify the central atom, count the electron domain, in this case 0 plus 5. So it's 5. So 5 is the hybridization of sp3d, and then the geometry is a trigonal by pyramidal. So check from the periodic table what is the total electron of phosphorus, and then write the electronic configuration, and then choose what is the autonomous orbital, how many valence electron, and then transfer into energy diagram. Okay, because of this one, the valence electron is 3 S2 3 P3. You can complete this electronic configuration of phosphorus, the valence electrons of 5. This is why we have 1, 2, 3, 4, 5. Remember, as I said, 3s, 3 third orbital ada 3s, 3p, and also 3p. This is why the energy diagram of the phosphorus, we have 3s2 and also 3 P3, 1, 2, 3, and the empty 3D orbital. The orbital is 10. This is why they have 5 boxes. 2, 4, 6, 8, 10. Ada 10 elektron maximum. So, from our observation, this molecule have to do the sp3d. If we not proceed the sp3d, only 3 single electrons available. So it means that only 3 bonding can be formed. So we have to migrate. We have to transfer the electron, one of the electron into the d orbital. So it becomes d orbital. And then we mix to produce hybridized is P3D. S3D. And then yang ini become unhybridized. So when we have these 5 single electrons available, and then we can complete this molecule. 1 with second chlorine, third chlorine, fourth chlorine, fifth chlorine. So we already complete the explanation bonding theory according to valence band theory. So the geometry is is trigonal planar. So P in the middle, and then we draw in the trigonal pyramidal way. So this is pyramidal. It's the same. This one with this one is the same. And then we overlap with the p orbital of chlorine. So Cl, you can complete the geometry. Cl, and then another Cl, and another Cl. Of course, the geometry is quite big because it's a PCl5, and then another Cl. Okay. So the overlapping area, spin up, spin down, spin up, spin down, spin up, spin down, spin up, spin down, spin up, spin down. So it should be overlapping between P with sp3, P sp3d, P sp3d, P sp3d, P sp3d. You have to label all. Okay, so it's look like this. Okay, okay. In order to form 5 covalent bonds with chlorine atom, phosphorus atom must supply 5 single valence electrons. This can be achieved using sp3d. The 5 chlorine atoms are covalently bonded to the phosphorus atom through the overlapping between the p orbital of chlorine and the sp3d hybrid orbital of the phosphorus. Okay, last example of hybrid orbital. This is the geometry. This is a molecular formula, SF6. So this is the Lewis structure. The central atom, 0 lone pair plus 6 bonding pair. So 6 electron domain. So 6 electron domain. The hybridization is sp3d2, and then the geometry is octahedral. So from the periodic table, identify what is the total electron of sulfur, and then write the electron configuration, and then identify the outermost orbital, and then you can get 6 valence electron. So this 6 valence electron, you can complete the energy diagram. 3s2, 3p4. So the outermost orbital, the valence electron is 3s2, and then 2p4. The one you have to complete first before you come to energy diagram. So 3s2, 3p4. So if we don't proceed with the hybridization, we only have 2 single electron. These 2 single electron only able to form the first fluorine, the second fluorine. The rest of fluorines are not bonded. This is why we have to hybridize kepada sp3d2. So in order to provide 6 single electron, we have to transfer this to D because we need D2. Then this one, this here. So sp3 d2, sp3 d2. The rest is remain unhybridized. So after we have 6 single electrons, so this one combined with that one share with this one share with this one share with that one share with this, and lastly this electron atom share with these electrons. Okay, so the geometry similar, sulfur in the middle, and then we have to draw the octahedral. This is the octahedral look like. Okay, because of the terminal atom is fluorine, so the fluorine it should be p orbital. Okay, p orbital. P orbital, and then p orbital, and then p orbital. Lastly, p orbital. Okay. All right. P orbital, p orbital, p orbital. So every electron domain, the region, they have up and down, spin up, spin down. Okay, and spin up, spin down. You have to draw it properly. Spin up, spin down, spin up, spin down, and also spin up, spin down. So according to the valence bond theory, this one is should be P with sp3 D2. Seems to here, same to here, same to here, same to here. Okay, alright, it's look like this. Some okay, some it's the same. Okay, so you can try drawing the shape of the sp3. Okay, so in order to form 6 covalent bonds with fluorine atom, sulfur atom must supply 6 single valence electron. This can be achieved by using sp3d2. The 6 chlorine atoms are covalently bonded to the sulfur through the overlapping between the p orbital of S with the sp3 d2 hybrid orbital of sulfur. Okay, so all right, we stop here for this video. The next video I will continue with the overlapping of atomic orbital in single and multiple bonding. It's talking about sigma, single bonding, 1 sigma, double bonding, 1 sigma, 1 pi, triple bonding, 1 sigma to pi. I will continue this subsection on the next video. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.